Hi AP Stat students, this is 7.3, the sampling distributions of X bar. So we're looking at means instead of proportions this time. We have a little simulation that is pretty helpful. So what I just did was I did one rep with down here in this first graph, I took a sample of size 5, and down in the bottom graph, I took a sample of size 25. So I'm going to do another one for you. Here's the sample of size 5, and I took the mean of that sample, and it drops down. And this is the sample of size 25, and we'll take the mean of that, and it will drop down. And then we could keep going. All of those things that dropped down are X bars. They're sample means. So if I take 5 of those at a time of each, we'll start building our distributions. I'm adding 5 X bars, 5 sample means at a time. So you can see as we're going that the one with the sample size of 25 is much more centralized, just like before. Even though it's 5 times larger, and then we'll do this 100,000, you can see that we're starting to get that nice symmetric shape. However, that first one isn't quite so symmetric. There's a little bit of a skew to the right there, and that bottom one is much more symmetric. There's hardly any skewness whatsoever. And it's important to note that I did not have a normal population. I had a very skewed population. This is where that sample came from. The mean of the sampling distribution of X bar is mu, that population mean. That's the population mean. This is the mean of the sampling distribution. The standard deviation of the sampling distribution of X bar is sigma of X bar, which is the sigma, this is the population standard deviation divided by square root of n. As long as the 10% condition is satisfied, there's that 10% condition again. So we have the central limit theorem. Draw an SRS of size n from any population with a mean mu and finite standard deviation of sigma. The central limit theorem, CLT, says that when samples are large, the sampling distribution of the sample mean, X bar, is approximately normal. Well, how large is large? So we're going to find that out. The sampling distribution of sample means will be approximately normal if the population distribution is approximately normal. So going back to our applet, if we have a normal population distribution, it doesn't matter how small this is. When I take my sampling distribution, or in this case a simulated sampling distribution, it will be approximately normal. You see there's no skewness. Or no matter what, if the sample size n is greater than or equal to 30, then no matter what or how horrible the population is, the sampling distribution will be approximately normal. And remember that one where we had n equal to 25 and it was very skewed? Well, it came out great. So n is greater than or equal to 30. The heights of young women follows a normal distribution with a mean mu of 64.5 inches and a standard deviation sigma of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches. This is chapter 2. Because this population distribution is a normal. So we want the probability that the woman is taller than 66.5. So we want the probability that our value is greater than 66.5. So that's about here-ish, making it up. So we want this area. So there's a 21% chance. So about a 21% chance that a randomly selected young woman is taller than 66.5 inches. But now we're changing it up. Find the probability that the mean height of a simple random sample of 10 young women, so that's n, exceeds 66.5 inches. So now this probability is the probability x bar is greater than 66.5 inches. Okay, instead of a singular value talking about the population, now we're talking about samples, and so we need the sampling distribution. Well, we know our sampling distribution is going to be approximately normal because our population was approximately normal. So no matter what size the sample, we're good. Mu of x bar is going to be about the same, 64.5. Sigma of x bar is that sigma over square root of n. So it's 2.5 over square root of 10. So 0.79. So now this is our x bar of 66.5, same kind of area. So I'm going to cheat it a little bit. I know everything's exactly the same, except my standard deviation is 0.79. So now it's much, much, much less likely. So less than 1% chance that I would get a sample that has a mean that high. Okay, which makes sense. If I get one girl that's 66.5 inches or taller, that's pretty common. But if I get a mean of 10 girls that are taller than 66.5 inches, that would be really, really rare. Your company has a contract to perform preventative maintenance on thousands of air conditioning units in a large city. Based on service records from the past year, the time in hours that a technician requires to complete the work follows a distribution whose density curve is shown in the margin. This distribution is strongly right skewed, and the most likely outcomes are close to zero. The mean time is up to 1 hour, and the standard deviation is 1 hour. What's the probability that it'll take the technician 1.1 hours to complete the work? I don't know. 1.1 is here, and let's say what's the probability that it would take the technician 1.1 or greater hours. So this area, I don't know that area because I don't know anything about that curve. I know it's really, really skewed, so I can't really do anything with this one. But in the coming week, your company will service a simple random sample of 70, that's my sample size, N, air conditioning units in the city. You plan to budget an average of 1.1 hours per unit for a technician to complete the work. So this is my average x bar of those 70. Will this be enough? Well, let's draw it. First of all, I know it's going to be a normal distribution because n is greater than or equal to 30. So even though my population was very skewed, my sample size is so large that by the central limit theorem, my sampling distribution will be approximately normal. The average is 1 hour. So my mu of x bar is 1 hour. And my sigma x bar was sigma over square root of n. So 1 over square root of 70. So 0.12. And we want to know, either way, we could say the probability that our average amount of time with the sample of all 70 will be greater than 1.1 hours, or we could say less than. Both will give us what we want. They'll give us an idea of what's actually going on. Since I've done greater than, let's do less than. So there's about an 80% chance that it will take less than 1.1 hours. So that's pretty good. So will this be enough time? It's really, really, really likely. 80% chance that this will be plenty of time.